All right, so our goal for today is to talk about capacitance. So capacitance is a property of kind of a system. So it is an intrinsic property, which is important because that means it only depends on its physical characteristics. It's a little kind of wonky to talk about because we're going to be looking at this from the perspective of parallel plates to start with, but that doesn't limit capacitance to parallel plates. Basically, any conductor, any charge can act as a capacitor on its own. So we're going to start with the parallel plates because they're the most straightforward to understand. Your derivation packet's going to go into other types of shapes. So we're going to look kind of at capacitors, and so capacitors have capacitance. So capacitance is something that has, capacitor is something that has capacitance. So whereas capacitance is the property. Capacitor is going to be like an object. So you can have like a parallel plate capacitor, which basically has like two plates that are parallel to each other. They generally have equal area plates. And they are separated by some sort of distance. You can have capacitors that are cylindrical capacitors. So like you have a charged wire with a another conducting cylinder around it. It can also be an insulator. It doesn't have to be strictly a conductor. It just has to be charged. So you could have kind of a setup kind of like that. I guess it would look like. That would become a better representation. And then you can also have concentric like spheres. So like this one is like inside, and then it could be inside a another sphere here where they have some different radii here, like R1 and R2. So those are all examples of capacitors. But even like an isolated sphere with a radius of R can act as a capacitor. A single point charge can act as a capacitor. You're going to have these two conducting plates. Okay, and they are going to have a surface area A, like I showed in the previous picture. And they are going to be separated by a distance of D. So they're going to be fixed in place somehow. The space in between the plates can either be empty or it can be filled. We are going to talk a little bit about what happens when you fill a capacitor, but if we assume that air is actually going to behave approximately like a vacuum, it's kind of a weird thought. I don't know how to spell vacuum. Is it 1U? Something like that. That air is going to behave approximately like a vacuum. So if they just show parallel plates and they don't tell you it's specifically in a vacuum, even if there is air between those plates, that's okay. But we're going to do things like put insulators inside of these plates to change the properties of the capacitor. So what happens is that there is some amount of capacitance for a parallel plate capacitor that is physically dependent on its physical construction. And we'll get to that kind of in a minute. But basically what a capacitor does is it stores charge. So these capacitors have a capacitance and they store charge. So how would they store charge? They basically store charge by creating a voltage difference between them. So here's what is going to happen. So I'm going to take this parallel plate capacitor, which is made of those two sheets. Okay, so like I said, there's actually two sheets here separated by a distance. They have a surface area A. We're going to assume that there's a gap between them. They're fixed in place so that it's impossible for them to move. Now in a real physical capacitor, capacitors will do things like catch on fire. And do crazy things like that. When you allow the plates to touch, they will also stop functioning after that point. So the fact that they are separated by a distance is important. So what's going to happen is I'm going to take this capacitor and it is initially uncharged. But these plates are still made out of atoms, so they still have positive and negative charges. So let's say that my plates are made of equal numbers of positive and negative charges, but their overall charge is 0. What we're going to do is we're going to take a battery, and the symbol for a battery in a circuit is a long line and a short line. We should remember that. And we're going to assume that this battery has some sort of potential difference. We usually call that potential difference this curly E. This E actually stands for EMF, which stands for electromotive force. So that's where EMF comes from, electromotive force. And the E comes essentially from the E here. And it is a curly E. It's actually the Greek letter. I don't know what Greek letter that is. Lowercase epsilon? So, I don't know. Doesn't matter. But you've got this battery here that has some sort of E. So we usually use E. Or sometimes we'll use V0 for like the battery, the capacitance of the battery. I mean the voltage of the battery, sorry, the voltage of the battery. It's important to recognize the different symbology because we're going to be talking about the voltage of the battery and we're going to talk about the voltage of the capacitor separately. But basically the way this battery works is it has an excess of positive charges on the long plate. We assume it has an excess of negative charges on the negative side, not really plates. But yeah, this is your electrolytic cell. You know, like you could make a lemon battery and you'd have like the copper electrode and the zinc electrode. So it could be any type of battery. It doesn't have to be some fancy battery. And then what we're going to do is we are going to take a wire and we are going to connect the conducting plates to each other by this wire. Now what's going to happen is basically these electrons that are built up due to the chemical reactions, like on the inside of this on the inside of this side of the battery, are going to repel each other, and they're going to repel each other so that they spread out along the wire. So we're going to add some extra electrons over to this side because we want to. This is going to. It's going to want to equalize so that its potential is constant across the conductor. We talked about that when we talked about the spherical conductors when you touch them together. So it's gonna want to equilibrate essentially by doing that. So these electrons are going to spread out along that surface. Now what's going to happen is that we're going to build up like a negative Q's worth of charge over on this plate. But what's going to happen is that those electrons over here are going to get repelled. So we're going to end up with these electrons leaving that plate and getting attracted over here to this positive plate. So they're getting repelled by the extra electrons over here. At the same time, they're getting attracted to this over here so that we are going to equalize on this side. Equalize. So we get V is constant on that side. So those are going to move. And then basically, this creates kind of like a temporary current in this circuit. So you're going to get a current in the circuit, which we're going to worry about actually the circuit aspects of this much later this year. But there's going to be a current that's going to flow. Now here's the thing. It's going to look like current is flowing through this capacitor, but there is no connection anywhere and no electrons flow across the barrier. Okay, so there is no electron flow. Okay, so the electrons cannot flow here. They're basically getting repelled across the gap. So that's a really, really important part of this to realize. Well, what's going to happen though is we're going to repel a negative Q's worth of charge, leaving a positive Q's worth of charge on this positive side of that parallel plate. So what we do then is this process is going to change and continue until we have a difference in charge, which means there's an electric field. So we'd actually have an electric field inside of here pointing from positive to negative. And if I have an electric field, that means I also have a potential difference. So this is kind of like in the electric fields lab where we created essentially two charged lines by connecting them to a battery. We were actually creating a capacitor, and that capacitor was storing charge. Now we say that this capacitor stores Q amount of charge. So this is an important distinction. So even though there's a negative Q over here and a positive Q over here, we don't say there's 2 Qs worth of charge stored. There's actually an amount of Qs worth of charge stored here. Now basically what's going to happen is that this is going to happen essentially until they equilibrate and they reach equilibrium, and then the current's going to equal 0. And when this current equals 0, what happens is the potential difference of the capacitor here, so we'll call this delta VC. Delta V for the capacitor is going to equal delta V for the battery, which we usually call E, okay, for the electromotive force. So we are going to end up with a potential difference, and this is a difference in potential between those plates, and we are going to store Q amount of charge. So this capacitor is charged when this is true. Okay, and then that charge is trapped there. So basically what happens if I disconnect this wire by unplugging an alligator clip or something, if this wire disappears, then what happens is that I'm left with this charged capacitor, and I have an electric field between the plates, I have a stored charge Q, and I have a potential difference. And then what experimentation has found is that the amount of charge that's stored, if I was to, say, charge this up to different potentials, so that if I was to have different amounts of voltages to the battery, so if I was to connect like a 3-volt battery and a 6-volt battery and then a 9-volt battery and a 12-volt battery, and I could figure out how much charge is being stored, then they figure out that that relationship produces a line with a constant positive slope. And so we called this value the capacitance. So the slope is capacitance. And the capacitance is an intrinsic property of this capacitor. So we can define capacitance as the ratio of Q to potential difference. Now make sure this is a delta V, not just a single V. Sometimes you'll see it as a single V, but really it is a difference in potential between 2 plates. Because I don't actually know what the absolute potential is of this battery. I don't know that this is 9 volts and that side 0 volts. All I know is the difference between them is 9 volts. So that's why we use the potential difference. So this gives us the idea of capacitance, where capacitance we can define as the ratio of charge to potential difference. Or if the way you really want to think about it, it's the amount of charge a capacitor can store and the potential difference is 1 volt. So we can kind of think about it like that. So the units of capacitance, if we look here, the units are going to be charge per volt. And we actually call that unit is going to be called the farad, after Michael Faraday, which gets the capital F for that unit. And our capacitances tend to be very, very, very small, so that our capacitances tend to be represented in microfarads, nanofarads, and picofarads. So micros, of course, 10 to the negative 6 farads. Nanofarads would be 10 to the negative 9th farads, and picofarads would be 10 to the negative 12 farads. So these will be very, very, very small values. And that's because the charge of 1 electron is very, very, very small. The charge of 1 electron is 1.6 times 10 to the negative 19th coulombs. So you can imagine that the units here are going to be very small. So you'll see microfarads, nanofarads, and picofarads very often. So you should be very familiar with those. What this idea of capacitance says is that if I basically have these parallel plates, These parallel plates, based on their physical characteristics, which we'll talk about what affects capacitance here in a second, are going to have some amount of capacitance, which we treat essentially like a constant. It is, for this particular system, it is a constant. Now, if I move the plates, if I make them bigger, smaller, that can change some of those characteristics. But once I have it set up in some particular situation, there is going to be a fixed amount of capacitance. And then basically what I do is I connect it to some voltage source, so that if, say, this was a 3-volt source and I had a capacitance, say, of, that'd be a huge capacitance, but if I had a capacitance of 1 farad and hooked up to, say, a 3-volt source, then what this tells me is it tells me how much charge that can be stored. Because it's easy to measure voltage. We can easily measure voltage. We just take a multimeter and put it to either side of the capacitor. We get a measurement. Capacitance is something that is experimentally determined, and are the capacitors that we use commercially, like in my SRD2 class. Those have printed values on their labels of what capacitance is, because it's an intrinsic property. So once you measure it, you've got it, and it stays that way. So what this would allow us to do is it allow us to find the charge stored on the plates, which would be C times delta V. So the charge stored on these plates is going to be 1 farad times 3 volts. So I'd have, in this case, 3 coulombs worth of charge stored. So this one would build up to a negative 3 coulombs. This would build up to a positive 3 coulombs worth of charge. If I were to replace this with a 6-volt battery, then I would get a linear increase, and I'd end up with 6 coulombs of charge stored there. So that's kind of how kind of a parallel plate capacitor kind of works, and how you would get it charged up. Now, what you would then do was, say, this charged capacitor, so let's say I charge it up and I disconnect it from the power supply, it's going to store the charge for a while. Now, there's the real capacitors, unless you could actually purely isolate this in a vacuum, then it can have the charges kind of move through the air and things like that. Or there's usually an insulator in here, like a piece of tissue paper in real physical capacitors, or an electrolytic solution inside. There will be diffusion just from the random Brownian motion of electrons on these plates, and eventually over time the charges will move and you'll end up with an uncharged capacitor. So capacitors are not really great for long-term storage. They're good for short-term storage. So like capacitors are used in things like AEDs and flashes in cameras, things where you need to be able to gain a certain amount of charge quickly by connecting to a power supply and then discharge that very quickly. So if, say, I wanted to light a light bulb, if I had a light bulb over here in the circuit, and then I connected the two sides, so what's going to happen is I've now created a path between the positive and negative plates, and so my electrons are then going to flow from the negative plate to the positive plate, which, as long as I get enough current, is going to cause this light bulb to light up. And that's kind of how the capacitors will be used. So then the question is, what determines the capacitance of a capacitor? All right, so what then determines the capacitance? So let's say I have this parallel plate capacitor right here, and I charge it up so that it has a potential difference between the plates equal to some value. I'll call it maybe delta VC for the capacitor. And it's done that by essentially putting a positive charge on, say, this top plate, and a negative charge, equal charge, on the bottom plate. So this bottom plate has basically a charge density negative sigma, and this has a charge density of positive sigma. Well, we've learned about these sheets before. We talked about the electric field essentially due to an infinite sheet. If I have an infinite sheet with positive sigma, then it's creating an electric field that's equal to sigma over 2 times E naught, okay? But I have the same thing going here, where essentially, due to this plate, I'm creating an electric field from positive to negative. And basically, this plate's contributing E equal to sigma over 2 E naught, and that's uniform, it's not dependent on radius. But then this guy here is also contributing E equal to 2E naught, so that the electric field magnitudes the superposition of those two charges. Then we ended up with our electric field here in the middle being sigma over 2E naught plus sigma over 2E naught. They're going to be the same direction. So this has an electric field of sigma over E naught. And you can derive that using Gauss's law, which I think is somewhere in your next derivation packet, or it's on an expert TA, or in one of the recitations. Will be there. You've already done it. We actually did it in one of the videos, but we'll do it. You'll see it again. It'll come up. So it's a good derivation to be able to do on your own. So I'm assuming that I have this electric field here. I also know that my electric field is equal to negative dV dx. So that if I wanted to find, say, my potential difference, I would assume that x equals 0 is going to be negative plate, and then this is going to be x equals d up at my top plate. So I would get dV is equal to negative E dx. And I'd assume that I have 0 potential down at the negative plate. That's the assumption we always make, is that our 0 volts is generally going to be down here. But even if it wasn't, you could assume that this is V1 and then this is V2, and then you would end up with just a delta V between them that's unknown. Actually, let's just do that in this case. So I want to integrate here. Let's sub in first. My electric field is going to be negative sigma over E naught times dx. Those are constant, so when I go to integrate, I just integrate between V1 and V2 via the bottom plate, via the top plate, and then I'm going to integrate over here from 0 to d. And I end up with, this over here, V getting evaluated from V1 to V2 is equal to negative sigma over E naught times x evaluated from 0 to d. So this is V2 minus V1, which is equal to negative sigma over E naught times d. So I end up with delta V equaling negative sigma over E naught times d, which basically just says that your difference in potential, that your potential is increasing in the opposite direction of the electric field. The magnitude of the potential difference is sigma over E naught d. So that's what the magnitude is going to be. But what's sigma? Well, sigma is the definition of charge per unit area. That's the definition of sigma. Well, the Q would be the Q stored essentially in the capacitor. It's basically how much charge has been developed on those plates. And this area is the area of one plate, not both plates. Well, both plates have the same area. So if we plugged in for sigma, we get delta V is equal to Q over A times D over E naught. And if we rearrange, we get that delta V is equal to E naught, Q D over E naught times A. So this is how much potential difference we have here. So basically the amount of the potential difference here is equal to Q D over E naught A. But we want to actually find capacitance. Well, if we rearrange this, we find that capacitance is equal to Q over delta V. So if I do that over here, I'm going to get E naught A over D is equal to Q over delta V. So that means E naught A over D is equal to the capacitance of my parallel plate capacitor. So C is equal to E naught A over D for a parallel plate capacitor. So that is something definitely to memorize. I believe it's also on the formula sheet. Now, this does have an assumption. Okay, so here we are assuming that this is an air capacitor, air or vacuum. Probably still spelling that wrong. So this is an air vacuum. If I put, say, an insulating material, like I said, we are going to do problems like that. But if I place an insulating material inside of here, then what's going to happen is that insulating material is going to cause a change in here, and we're going to find that our capacitance is equal to some constant times E naught A over D. We're going to talk more about this tomorrow, but this constant is based on the material in between, which we call a dielectric. So kappa for air and vacuum is a 1, essentially. So that's why these are equivalent equations. This one just covers more cases where it's not just air in between those plates. And once again, this is only for a parallel plate capacitor. You're going to do derivations for cylinders and spherical capacitors later. So looking at this equation, this actually tells us a lot about the behavior of parallel plates and what can affect capacitance. This tells me that capacitance is proportional to my surface area, and my capacitance is inversely proportional to the separation distance. So if I were to make bigger plates, then I would end up getting a larger capacitance, which just makes sense. At the same voltage, I could store more charge because I'd have more surface area for the charges to get added to before they repel each other to the point where they can't add anymore. With the separation distance, if you think about it, if I make the plates closer together, so if I put them really close together and I make that separation distance smaller, then the electric field is going to get stronger. Because remember, the electric field is the potential difference is equal to E times D for a parallel plate. So if I separate the distance but keep a constant voltage for the power supply, then I'm going to get a larger electric field. And a stronger electric field means I'm going to be able to attract and store more charge. So you're going to get a larger capacitance. Now, the thing you have to be careful with this is how do you add or remove, how do you make these changes? Because they're going to ask you questions like, okay, so this is connected to a battery. So you have a battery connected here, and then I separate the plates. So you have to be careful because these two equations get used together. So if I'm still connected to the battery, then my voltage is a constant. This also gets used. If I'm not connected to a battery, then charge is constant. So if you are connected to the power supply, so if you're connected to the battery, then in these equations, your delta V is a constant. It's going to equal whatever the voltage of the battery is. If you are isolated, so it's not in contact with the battery, then your charge is constant. We assume that the charge cannot diffuse across space and that we'll keep a constant charge in an ideal capacitor. So that'll change the relationships between the variables here. But these are like your 3 most important equations. And you can expect to see lots of questions about, okay, you have an isolated capacitor and you double the surface area. What happens to the electric field? Or you have an isolated capacitor and you double the surface area. What happens to the capacitance? What happens to the separation distance? Those are the types of questions you're going to see. So those are types of things that you should practice. You'll see those in a lot of practice AP test books. Very, very common. So that's an introduction to capacitance. We are going to talk a lot more about this dielectric, this material in between. We're also going to talk about what happens when you make arrays of capacitors, when you put capacitors in series and parallel. We're going to talk about the energy of capacitors. So we're talking about spherical and cylindrical capacitors, lots more things going on.